Good afternoon. Thank you for coming. My name is Miguel Yaller, as you know. It's with great pleasure that I introduce you today to Professor Reza Akhavian. He's an assistant professor at Cal State East Bay in the construction management in the School of Engineering. His interests are data management, data analytics, machine learning, big data, for applications into engineering and construction management. So we have a good opportunity to learn some of the tools that are being used and that we actually want to develop as part of some of our projects. I met Reza about 2 years ago when we spent a week, a really intense week on teaching, kind of a teaching school. We participated in the ASC Exceed program that I haven't worked that much in my life for a long time as that week. So we had to work like from 7 a.m. until 11 p.m. We had to present several topics. We had to have critical reviews. It was kind of interesting having to teach to teachers and then compare our ways of teaching, and you realize that you don't know anything. So hopefully after that, my teaching improved, and I hope your teaching also improved after we took that teaching course. So now we have Reza. Thank you for coming and accepting our invitation.
Hello? Can you hear me? Good? Okay. Thank you very much, Miguel, for the introduction. As Miguel said, my name is Reza Akhavian. I'm an assistant professor of construction management in the School of Engineering, California State University, East Bay. Thank you for inviting me. A full room full of students. That excites me, and I don't get much credit for that because I heard it's a mandatory class for you guys. But I'm still happy to present to you guys. A little background about myself. I got my bachelor's, master's, and PhD in civil engineering. My graduate studies was concentrated on construction management, and basically my research was on the applications of information technology, automation, robotics, and towards the end, machine learning, data analytics in construction engineering and management. And what I'm going to present today is basically what I have done during the last 2-3 days after, towards the end of my PhD dissertation and then after graduation in my research as a faculty member. I would like this session to be an interactive one, so please stop me whenever you have a question, and we can discuss your questions in an interactive session. I'll start with an introduction. I'll talk about my previous work, where we started this research and what was the problem statement, why we wanted to achieve what we achieved. Give you some background on construction, similarities between construction world and transportation world. Then I'll talk about the methodology of the research. I will explain and describe the real-world experiments that we conducted for construction equipment, for construction workers separately, and the results for each. And then I will dive into the applications in transportation and transit world. So hopefully you guys can pick or take away what is applicable to transportation, to your research from this presentation. So, a brief introduction about construction, which probably you can find similar aspects to transportation systems. In construction, you usually, when we talk about a construction job site, you are imagining a messy environment, something like this. A lot of workers are interacting with the equipment, with the materials piled up in the storage. And basically, you're dealing with a dynamic environment Everything is constantly evolving, and there is supposed to be a plan. There's supposed to be a schedule, but it's never based on the plan. It's never based on the schedule. There are always change orders. There are always changes in the cost, the final estimated cost, the schedule. When I say never, it's probably a little bit of exaggeration, but most of the time it is not what you expect. And that's because of all the uncertainties that are involved in the workflow, internal uncertainties. You have labor strikes. You have a piece of equipment that is broken down. You have different, again, internal problems and internal challenges. And then you have external unforeseen conditions. You have the weather condition that doesn't go the way you expected, because most of construction projects are outdoor, right? And again, in general, you're dealing with an unstructured environment. That I think there are a lot of similarities between these such environments and those that you see in transportation systems. Again, a dynamic system, probably more structured than a construction job site, but the behaviors are uncertain. The whole system is dynamic, and so you can start thinking about this similarities between construction and transportation. So automated data acquisition is used in this research as an efficient way to collect information, extract relevant knowledge from the data that we collect. We are specifically interested in collecting data, analyzing those data, and then extracting knowledge out of those data that we collect from constantly changing environments with constantly changing data parameters. And we are dealing with a large volume of data, which is now called big data, the notion of big data. What is big data? Can someone give me a definition? Raising your hands? Yes. Over two. I have never heard a number about that, but that's good. Yeah. Good. Yeah, I heard that. Yes.
I would say it's the idea that you can collect data in ways that have been really practical for a sense of both literal scale and big data, but also the different sorts of data that you can collect and also the breadth, not just depth, but the breadth also.
Exactly. Well, there is no certain definition or exact definition, just like what Nick mentioned. There are no numbers that you can say that over this number is big. If it's less than this number is small data. I've never heard about small data. So nobody actually knows what is big data. Whatever that is big and you cannot fit it in a spreadsheet, probably in Excel sheets maybe, is big. As long as you can analyze those data and you can get meaningful information and extract meaningful knowledge out of those data. And as long as they are not a few data points, people tend to call it big data. And so, we are not here to define what is big data, but the fact is that because it's a hot topic right now and it's very trendy, we can call this kind of research, again, part of the big data domain. Okay, but again, it doesn't really matter. So, going back to the discussion, data analysis and knowledge extraction in a dynamic environment, as those seen in construction job sites or transportation system, it is obviously not a trivial task. The data collection is not trivial, it's not easy. The data analysis is not easy, and then getting or having meaningful information, meaningful knowledge, meaningful and interpretable knowledge for computers is not easy. In construction, different application areas to evaluate the productivity of your construction projects. You can use data for that. You can compare today's progress with yesterday's, and that is called progress monitoring, to see how much progress you've made. And that can happen through data collection or automated data collection. Another example. Then construction industry is a big contributor to greenhouse gas emission. Production of cement with the giant construction, heavy equipment. So again, there are opportunities to contribute to sustainability and reduce from the greenhouse gas emission. And I have worked on all these areas, but what I'm focusing on right now is this safety and health improvement in construction that I will focus on more, which is, again, very important. Construction is a very dangerous industry, second most dangerous industry in the United States, and so that's another application. I want to give you a little bit of technical background about how we started this research, and by we, I try to give credit to my PhD advisor. Make sure that you always do that. Why this research started and how we started that, and then it turned into a new paradigm of research. But initially, at that time that we were thinking about that research, data collection was usually exclusively using GPS data, position data. We thought that it might not be enough. We can use different modes of data. We can leverage different types of data to get more accurate information and extract more accurate knowledge. We added different modes of data, such as the orientation data, orientation of the, for example, this arm of a front-end loader, of an excavator. Weight data on the bed of dump trucks, for example. We added these modes of data. We had data fusion and mining algorithms to blend these data and extract operational knowledge. So position data, orientation data, load data. We thought that, okay, if you use only position data, you may think that whenever the position does not change, that piece of equipment is idle if you're collecting data from construction equipment, and whenever it moves, it is working. Then it turned out that no, this is not the case. Maybe it's still it's stationary, it's fixed. It's a dump truck that is unloading its load. It is working, but it's not moving. So we can actually take advantage of the different types of data that we're collecting to be able to identify the state, whether that piece of equipment is idle or if it's busy. If it is idle, is it out of service or is it waiting in a queue to be loaded by an excavator? If it is moving, is it really working? We don't know, just by the GPS data. So that's how other modes of data can contribute. Some other pieces of knowledge that we could extract was we are collecting data in an automated fashion. We want to reduce the supervision of human as much as possible. So one thing that we could get out of this data was approximation of the work zone vicinities of the construction equipment. We know that construction equipment spend most of their time in some specific designated areas. Let's say there is an earth moving operation where you need to load earth, soil, with an excavator, unload it on a dump truck, and the dump truck needs to haul and take this soil, dump it somewhere else, right? Imagine this scenario, and we're gonna talk about this example, specific example more. But that piece of equipment, that truck, spends most of its time in somewhere that is called loading area. Here, it's being loaded by this excavator. So the data that we collect with a specific frequency, the position data here that we collect, have high density in these two areas, in the loading area and in the waiting area where the trucks are waiting. In this hauling routes, we have lower intensity of data. So again, these are some of the basically notions and some of the hints that we could get, and we can have rule-based algorithms to detect work zone vicinities. Again, another piece of knowledge that we could collect and we could have from the data that we collected. How we did this, the background is a k-means algorithm. This is the mathematical background for those who are interested. I leave it here, and I think the presentation will be shared with the audience later on, so you can have access to this. This is an unsupervised machine learning algorithm. K-means is an unsupervised machine learning algorithm, and we use that. In addition to the two dimensions of x and y, we also added one more dimension for this specific experiment. We added the weight dimension, the weight of the bed of the dump truck, so we could distinguish more between different points that we detected through k-means. And the last piece of information or knowledge that we detected was activity durations. Again, it was a rule-based framework, a rule-based algorithm for the dump truck and for that loader. In that specific example, we said, okay, we have position data, weight data, and the angle data. Is the position changing, or if it is fixed? Is it moving or idle? We have the position, we have sensors on both the dump truck and the excavator. Are they close to each other or not? Based on these semantics, based on these rule-based taxonomies, we could detect, okay, if that piece of equipment, if that dump truck is if this combination holds true, then we realize that the dump truck is in the loading area. When we know that it's in the loading area at this point, it's time-stamped. We know that like 5 minutes from now it's in the dumping area. Then we can basically find out what is the hauling activity duration. So you got the point. This is a very simple example of how it worked. Okay, so again, activity durations, work zone vicinities, state of the equipment. These are some of the key information that we needed in order to see if we can improve the performance or the productivity in a specific construction project. One more piece of information was related to the queue formations. Again, I think that has a lot of applications in transportation. You would like to know the inter-arrival times, the queue discipline. Is it FIFO, first in, first out? Is it last in, first out? And what is the service time? So we conducted similar experiments, and we collected the same data. And we saw that, yes, we can collect this data with good accuracy. We can extract this knowledge with good accuracy, and we can actually use those. So we collected all these data, and we ran some experiments with these toys of mine. We had sensors on these toys, on these remote control construction equipment models. And we used all these things that I have mentioned so far. This was in our research lab. We had ultra-wideband sensors and receivers on the ceiling. We had tags on this construction equipment toys, so we can track we didn't use GPS. We couldn't use GPS indoors, so we use ultra-wideband and with the other sensors that we used. Yes. Yes. Exactly. So you determine those zones. Once you have those, then you can determine, okay, what was the duration of that specific activity in that zone? What is the duration between these two zones? Yes. Good question. Okay. So just one of the experiments, we have done a lot of experiments. One of them, we had just one loader, multiple dump trucks. We wanted to see if we give priority to one types of the dump trucks. We had big dump trucks and small dump trucks. I think we had so for example, these are the big dump trucks. We had the small dump truck here. If we give priority, can we extract this knowledge out of the data that we collect? Can we understand there is a priority in the serving in giving service to these dump trucks? So we try to make it a little bit more complicated with giving these with defining these different conditions. And we also included a service area, not a regular earth-moving operation, We also have a service area, so they can be in the loading area, in the dumping area, in the hauling route, or they can be in the service area where the equipment requires some service. And again, this is the result of the K-means with the third dimension, with the weight dimension. And so we modeled this experiment in a software called the stroboscope. It's a specifically designed programming language for simulation for construction. And this is the activity cycle diagram of stroboscope for different resources and different activities that is shown here. And this is a piece of code in that platform. For example, the discipline, which is a Q discipline, in that specific example was defined by the size of the dump truck. This shows that. And here are the simulation results based on our preliminary experiment. So we have 4 different measures, 4 different quantities that we wanted to compare between the results that we got using the data that we collected. Let's call it a dynamic simulation. The results that we get if we have used a static simulation with the predefined activity durations, with predefined or subjective information such as activity duration, and what happened actually in reality. So what happened in reality is this first bar in all 4 charts. The result of the data-driven simulation or dynamic simulation is shown in this lighter bar in the middle, and the lightest bar is the static simulation. So the 4 measures are total moved soil. We wanted to see we have the actual total moved soil during the experiment. We wanted to see if the simulation using data-driven simulation is a data-driven simulation closer to real-world measures or the static simulation. So the result that we got was that for all these 4 measures, total moved soil, loader idle time, total operation time, and total equipment cost, again, these are simulated, for all measures, the result of the data-driven simulation is closer to reality. Actually, that real-world measures are all in one standard deviation of the data, the result that we got from the data-driven simulation. So that was our first hint that, okay, this works. If you collect data in real time, and if you apply the data that you collected from the same project on the exact same project, then the results that you get through a simulation where you can simulate, predict the loader idle time, the operation time, equipment cost, how much material you can move, how much soil you can move, is going to be more accurate. Okay, so we considered this and we took this as a positive sign. Then we thought, okay, what about collecting different types of data? That is easier. Putting sensors on the dump truck bed is not easy, and it requires a lot of maintenance. It's a construction site. Putting orientation data or sensors and collecting orientation data might be, again, difficult because it's in a construction job site environment. We thought, let's think about different types of sensors. Let's talk about more pervasive sensors. Let's see if we collect different types of data, we can extract similar knowledge or similar information out of the data. A given smartphone that you all have has a host of different sensors. It has accelerometers, gyroscope, magnetometers, GPS, proximity sensors, NFC sensors, near-field communication. We specifically focus on 2 of them, the accelerometer sensor and gyroscope. Accelerometer, gyroscope, and magnetometer are usually called IMUs, inertial measurement units, that we have in all the smartphones. When you're looking at a video on your smartphone and you tilt it, the video tilts as well. That's what the accelerometer does. That's what the accelerometer does in your smartphone, or the IMU sensor, all 3, does in your smartphone. So we thought that maybe each activity in a construction job site has a specific pattern in the data that we collect, in the accelerometer data and in the gyroscope data. Maybe there is a signature for this operation or this task in this operation that distinguishes that with the other task in the same operation or different operations. We wanted to test this hypothesis. This is not a new field in computer science. The oldest research studies that I saw using accelerometer and gyroscope in smartphones date back to 2010, 2011. In more structured environments where, for example, the subjects were walking, jogging, going up the stairs, going down the stairs, so on and so forth. Again, some applications for transportation or pedestrian, for example, behavior modeling. But this is, again, something that is not new in computer science. We borrowed this basically concept from computer science, and we came up with this methodology, with these building blocks for a system architecture. We said we can collect data from construction equipment or construction workers, and that data is IMU data, inertial measurement units. We need to prepare those data. We need to clean those data and work on the data that we collect a little bit, and prepare them for extracting some features. We wanted to use machine learning algorithms. We wanted to train computers to be able to understand that specific behavior, to be able to detect that specific mode, to be able to detect that specific area of operation. So because we wanted to train, we had to basically convert the data, the raw data that we collected, into interpretable knowledge for the computer. So that is the feature that computer can understand from the data that we prepare. So data preparation, feature extraction, we annotate the data, we label the data. If we collect this data with this in this range, accelerometer data or acceleration data in this range, let's call it hauling. If we collect accelerometer in this accelerometer data in this range, let's call it loading or unloading, right? Different labels we assign to the different types of data that we collected based on these are the training data, the data that we collected to train an algorithm. Using the features and the annotated data, you train machine learning classifiers. You assess your model to see how well that model can predict. Unseen examples, you train your model with the training set, and then you have a test set that are the unseen data. And you want to assess the efficiency and the successfulness of the model in detecting and predicting. And then you have the activity recognition results that you want with some accuracy that we'll talk about. So part of the real-world experiments, we put sensors on the windshield cabin of a front-end loader. We actually use two smartphones. It doesn't really matter if it's an iPhone or if it's an Android system. We just wanted to make sure that it's very difficult to get access to construction job sites to do these kind of things. So that was why we wanted to have a backup. So we put two smartphones. These are the data that we collected in our very first experiment. Accelerometer data in 3 axes, X, Y, and Z. The gyroscope data, again, in 3 axes, in X axis, in Y axis, and in the Z axis. The sampling frequency that we used was 100 hertz. We segmented the data into 128 data points with 50% overlap. Again, this was borrowed. Why 50% overlap? Because it showed the best performance compared to 30% overlap or 70% overlap in activity recognition in computer science. So we borrowed all these from computer science. We extracted 7 features from 2 sensors, accelerometer and gyroscope, in 3 axes, X, Y, and Z. So in total, we had 42 features. And because we were doing this for the first time, we didn't know which machine learning algorithm can yield the best result. We used 5 machine learning algorithms. We used neural network, we used decision trees, k-nearest neighbor, logistic regression, and support vector machines to see which one. It wasn't really important to optimize one of these. We wanted to see which one performs better so we can focus on that one. Again, some technical backgrounds on what we used in each one of these algorithms. What was the activation function for the neural network? For the decision tree, what was the optimization criterion? For K and N, the distance function was a Euclidean function, logistic regression, what was the cost function, and for support vector machine, what was the kernel function that we used. Again, these are some details for interested students who can later on take a look at these details. So we also realized that we should consider a level of detail. How detailed you want to extract those activities. In what detail you want to extract those activities. Is idle or is engine off or engine on enough? Is this what you're looking for? Or you want to know if engine off and then in the engine on, is it idle or busy? That's the second level. Or when the engine is on and it's busy, is it moving and scooping, for example, that I'm talking about the front-end loader, by the way. So if that front-end loader is moving and scooping, or it is moving and dumping, for example, these sorts of activities. Or even further, you want to separate those two activities, moving from scooping and moving from dumping, right? So we wanted to consider different levels of detail in recognizing these activities and doing or performing these activity recognition. So again, the activities per each class, these are here, they are tabulated here, number of segments and number of instances in each segment for each class of data. Our we had level 2, level 3, level 4, 2, 3, 4 in our experiments, where we had 3 classes in level 2, 4 classes in level 3, and 5 classes in the 4th level. This is the preliminary result for the 3 levels, for the 3 levels of classes, and the 5 classifiers, 5 machine learning algorithms. We realized that overall, neural networks had the best performance, and again, we tried to tweak these algorithms as much as we can, but it wasn't really important that we optimize or we maximize the accuracy in one of them. We wanted to see which one has the best performance. From that point on, we wanted to focus on that one. So neural network showed the best performance. We focused on neural network from that point on and used neural network. Some sensitivity analysis on the number of data points per window. So we picked 1 second and 28 hundredths of seconds, 1.2 or 128 data points per second with the 100 hertz frequency. But we just wanted to make sure that that yields to the best accuracy. So we considered also 64 data points per window and 256 data points. And why they are power of 2, that's a long story, because we use fast Fourier transform to transform the statistical time domain features to statistical frequency domain features, right? So that was why, and then again we realized that our initial choice of 128 data points was actually the best one, with very little difference in the accuracies that we got. And here are the results. So for level 2, 3 class, engine off, idle, and busy, this is what is called a confusion matrix. A confusion matrix is a square where you show it has different boxes inside, a number of boxes, and you show the predicted classes in rows, in columns, and the actual classes in rows. So if it was actually A, activity A or engine off, and it was predicted as A, then it shows like 98% accuracy. If it was actually A, but it was predicted C, I mean there was 2% of the instances that were A, but they were predicted as C. So we want this diagonal being the darkest possible, right? So the darker the diagonal is, the better the accuracy in each specific activity or task. So very good performance and accuracy in with 3 activities in level 2, 98, 92, and 99%. When we move forward, level 3 with 4 activities, the accuracy tends to drop So 96% for the engine off, and then the idle mode, moving and scooping and moving and dumping. You can see that in the last one we have as low as 70%, and it was mainly confused with the activity moving and scooping. So moving and dumping was confused with moving and scooping. That was expected. And then lastly, the one that level 4, that we have 5 activities. Again, you have a very good accuracy here, 94%, but you have accuracies as low as 35% here, where it was actually confused with another activity even more. Yes.
Just looking at this one and the last one, do you have any idea why it might be that that predicted in this case D for D way more frequently than predicted D for D? Like those are two things that it should use.
Yes. Well, D and E here are moving and dumping. The movement of that specific equipment should have been the same in these two cases. So what we have is the movement of the body of that equipment. This is all the information we have and we're using here. If we have used another mode of data, we probably could have gotten a better accuracy here. But with just accelerometer and gyroscope, they have been confused. Why? Because probably the movement of the body of that piece of equipment was the same in these two cases.
Right, but why is it, like for example, if it guesses dumping while moving 70% of the time, then why is the reverse not always right and always so accurate in guessing when it's moving? Why is that one 96%?
Here.
Like why is the reciprocal not true, I guess?
Yeah, that's a good question. It doesn't have to be. So based on, I don't know the technical answer to this, but from the experiments that we did, that doesn't have to be the exact same. The reciprocal shouldn't be the exact same accuracy. It might be, so we pick, the training data that we use is picked randomly. So maybe it was different in this case than this case. So I totally understand what you're saying, but I don't have an answer for it now. I can double check this. Good question, very good question. So this was the last experiment with the most complex sort of number of activities that we performed for construction equipment. Then we moved forward. We said, okay, why not for construction workers? Let's try it on construction workers. We should be able to, with a little bit of modification and adjustment, but with similar algorithm, we should be able to collect data, prepare data, extract features, label those data, and recognize activities for construction workers. So we did some, again, these are experiments. These are not real-world construction workers. These are a bunch of graduate students in our lab. And then we asked them to simulate some specific construction activities. We asked them to saw, we asked them to hammer, we asked them to haul using a wheelbarrow. Okay, and so we collected number of data for each activity. We categorized them in 3 categories. First category, sawing, and when we say saw, we wanted to see how well we can distinguish between doing the actual sawing or doing nothing. So sawing and idling. Then in the second level, we had 2 activities that specific person was doing: hammering and turning a wrench versus idling. So 3 total tasks: hammering, turning a wrench, and idling. And we thought that because we put the sensors or smartphones on the arms, we thought that the activity or the movement of the arm in these 2 activities might be similar. So we wanted to confuse our algorithm as much as we can, so we see how accurate is the detection. And then the last category was loading, pushing, unloading, and returning, and that is with regards to those wheelbarrows. Again, we used 5 classifiers. We wanted to test all 5 classifiers in this case as well to see if neural network has the best performance again. And we use 10-fold stratified cross-validation. In the first category, the results was astonishing, very good, 100% for sawing. In the idling, it was 90%. So it was expected. You are either sighing, so this is actually working, I mean this is moving, or you do nothing, so your smartphone does not move. So I would have expected a 100% accuracy here as well. But that's still good. And in terms of the classifier neural network, decision tree, KNN, logistic regression, SVM, for the training and cross-validation, testing accuracy, again, neural network showed the best performance, and what we care about is the tenfold cross-validation. The training accuracy is not really important. Second category, hammering and turning a wrench. Again, 95% accuracy for hammering, 95% accuracy for turning the wrench, and in the idling we had 82% accuracy. Neural network showed the best performance again here, and lastly we had this activity, this category basically with these 4 or 5 activities in it. And again, because we added the number of activities, we are reducing from the training data in each category. Then the accuracies dropped in some specific activities. So overall, we realized that this is actually working in construction. We can use it for detecting activities and basically use it in different application areas. What we focused on was using this for productivity. What I am using at this point in my career is using these types of data for ergonomic analysis, for safety and health analysis for construction workers. So per OSHA, Operational Safety and Health Administration regulations, for example, the construction workers cannot stretch his or her hand for more than 2 minutes, let's say. You can detect with these smartphones that they carry if this is happening for more than 2 minutes, and you can send them an alert that this is not safe, this is not ergonomic, something like that. Or if you can detect activities, if you have this system on both the workers and the equipment, you can detect if they are entering a dangerous, hazardous zone, for example. So for safety zones, these have some applications, and these are the things that we are working on. Now, yes. Exactly. Yes, that's what we did for a neural network. When we realized that neural network had the best performance, we used the training data to tune the specific parameters that could change the result. And for some of the other algorithms as well. For KNN, for example, you can change the K to see if you get the better result with different Ks.
But shouldn't the approach be like that?
In order to make it unbiased, if you use the 10-fold cross-validation or n-fold cross-validation, you're taking one of the 10 parts and you're training it, and then you're testing it on the remaining 9 parts. So you're basically taking care of that bias. And you test it on the 10th part. So you're taking care of that bias in that step. You can do that as well. That's another way of doing that. But what we did, we trained the data. We realized we used the algorithm that showed the best performance with the parameters on the training data, and then we tested using tenfold cross-validation on the testing data. Does that make sense? But what you're saying is absolutely correct. You can do that as well. Okay? So that was the overall idea in construction. Now, we would like, together with some of my colleagues, including Miguel, we want to explore these ideas in transportation. So I was digging the transportation literature. One of the oldest applications that I could find in the transportation area was using what dated back to 2010 in the ACM transaction on sensors networks, and they were some of the UCLA folks that used mobile phones to determine transportation modes. Now, The most frequent application of this algorithms or this kind of frameworks in transportation is detecting transportation modes. So I tried to list the objectives, the methods that they use, and the results that they achieved for each one of these applications, and I outlined some of these papers and some of these studies here for you guys. So their objective here was to detect the transportation mode of an individual when outside, whether that individual is stationary basically, or walking, running, biking, or in a motorized transport. And you can see that different modes basically have different patterns in the data that is collected through the accelerometer. And these are the results. I mean, they could achieve 93.6% on average for 16 users in terms of detecting the transportation mode. Couple of other examples for detecting the transportation mode. Again, this example published in 2015, they wanted to develop multi-class classifiers that identify transportation mode. In this case, driving a car, riding a bicycle, riding a bus, walking, and running. And they used similar machine learning algorithms in addition to random forest. And here is their results. They could achieve up to 95% accuracy this is the precision and recall result, but the accuracy that they received, the highest accuracy that they got was 95%. These two examples, this one is also transportation mode detection, but this one here, they tried to use similar algorithms, similar frameworks for a warning system, for creating a warning system. So they had 3 levels of activating that warning system, then basically computing the risk, and then giving warning to the user. So that again is another approach. The objective was to create a warning system on smartphones to protect vulnerable road users like children and elderly. What they used was not actually IMU sensors. They used GPS and 4G communication. And their result was like 96% accuracy in detection. And lastly, one of the most important applications of this that I'm also exploring is using smartphones to detect fuel consumption and greenhouse gas emission. So that study was performed in 2016. They had 3 objectives: detecting the modes, again, evaluating the effectiveness of fuel consumption and CO2 estimation, and also developing a shortest path algorithm for finding eco-friendly routes in near real time. None of these applications, as far as I saw, are in real time, and most of them, I mean, are in near real time. And their accuracy in detection was 95%. The fuel consumption estimation accuracy was around, the error in fuel consumption estimation dropped by 15%. And they could also find the SP, the shortest path for minimizing both the travel time and fuel consumption for a given network through this types of framework. So in conclusion, we tested the use of these low energy sensors, MEMS sensors, in construction applications. And with this recent advancement in machine learning, nowadays we have this deep learning algorithms and convoluted neural network algorithms that are much more powerful than the regular neural network algorithm that, for example, I used in my research. So they are much more powerful in detection and prediction, and I bet that the confusion matrices that they can produce are all black and dark in the diagonal. So our experiment in construction validates the effectiveness of such frameworks, but we see a lot of potential applications in construction that can benefit from such applications in transportation and transit systems, for transportation planning, for risk mitigation, and GHG emission estimation. And I'm here to hear back from you guys, your feedbacks about what you can think of in terms of the applications in transportation and transit. With that, thank you very much. I listed the references that I use and also some of my publications that you can refer to at the end of this presentation. and the floor is open for your questions. Yes. Thank you. In construction? That's a great question. That's something that actually we had a meeting yesterday with my research group, and we were talking about that. Construction is moving to a newer stage, to a new stage that is prefabricated construction. So quality assurance is very important in that regard, and this is actually something that we are going to look into. No, we haven't looked into that area yet, but this is something that we want to explore in near future in our research group, actually. That was a good question. Thank you. Oh, yes. So the question, I forgot to repeat the question. The question was that if we have explored this framework, the application of this framework in quality assurance and quality control in construction. And so not yet, but we're looking forward to doing that. Thank you. Thank you. So the question is that if we have applied this framework or these kind of frameworks on the intersection of construction and transportation. We submitted proposals, it got rejected. So we had some ideas to apply that in the applications, intersections of transportation and construction. One is for the safety zones. If we have a road work in progress, that we thought there are potentials in that area. The other thing that is not really related to construction, but Caltrans is trying to remove as far as I know, correct me if I'm wrong, the gas tax, and they want to charge based on the mileage that each vehicle basically travels. And we try to apply this concept on that in order to be able to predict or estimate the mileage. That was a proposal that was rejected. So we are thinking about different ways of applying that in transportation, because this is one of my favorite areas of research. But these are the ideas that we have. We haven't really explored them in detail. Yes. Uh-huh. Mm. Great question. So the question is that if we have explored the applications of this in reliability management, and whether we can detect the failure time. I haven't explored that. I haven't seen any study on that. Reliability management is a big research area in construction, but these are all very good. I hope this is recorded so I can use these ideas later. But this is a very good area of research that we can potentially look into. Reliability management, again, this is very new in construction. Construction is very reluctant in using technologies. I'm currently working with a construction job site as a construction company as a consultant. They are very unwilling to do something new. The superintendents, the project managers, they want to continue what they have been doing for the last 10 years, and they said, I know what I'm doing, and I don't know anything new, so please let me alone. Let me do my work. just imagine, I cannot imagine I ask their workers to put their smartphone on their arms and let me track you. They hate that. So there are a lot of applications that we can explore. As you said, reliability management, I think, is a very good area in addition to QA, QC, quality assurance and quality control of construction. But no, I have never applied that in my research. Yes, sir.
Kind of piggybacking on these other two questions as well.
Mm-hmm.
One of the things that you talked a lot about was how the advent of smartphones and ultra low cost, low energy sensors helped really enable a lot of your research. Where do you think that a lot of the other, like the wearable smartwatches with things like a heartbeat sensor, possibly an O2 saturation, and other sort of biometric sensors, where does that data fit into, and especially for construction? How does that all fit into what you already do?
Great question. So the question is that we collected data using smartphone sensors. How about collecting them with wearable sensors? Fitbit, for example, or different types of wearable sensors, right? That's the question.
Or Apple Watch, and then how does the biometric side of that all?
Okay. So, and also using biometrics. So, actually, this is something that we have explored, and I have collaborators in Texas A&M that are working on this. I haven't started that experiment. I recently purchased wearable sensors and EMG sensors to try that. One of the potential other potential sensors or hardware that we want to try is heart rate variability and heart rates, basically data that we can collect and we can feed into the machine learning algorithms to increase the detection accuracy. Now, why we use smartphones, the goal was twofold. We wanted to see that was pervasive, that was available. Everyone had a smartphone, and I had a smartphone. I didn't have to buy separate sensors. So we wanted to see if accelerometers and gyroscope work in this context. But at the same time, if smartphone accelerometer and gyroscope work in this context, right? So that was probably a proof of concept experiment that we did with accelerometers and gyroscope. Right now, construction startup companies are trying to develop hard hats or vests that have these sensors embedded and use those and basically run similar experiments or detect similar activities for their own purposes, right? So yes, we can use those type of wearable sensors and we can collect different types of data, such as those that you just mentioned. But this is again a research in progress, and we will look into it definitely. Thank you. Other questions? Yes. Yes, so the question is that how this work is related to IoT and the Internet of Things. I don't know about C3 IoT. I heard it in NPR, I think. Hmm? Okay. This is, I assume this is categorized as an Internet of Things application. Whenever you have a network of sensors and you collect data and you try to extract knowledge from different nodes, right? And these different nodes can communicate with each other. This is loosely defined as Internet of Things. So we are doing similar things here. We try to make this communication between different construction workers and the construction workers and other entities in the job site, such as the construction equipment. Now, there are research groups, there are research prototypes that had tags on the materials as well, so you can have that interaction between the worker and the material as well. But this is, I think you're right, this is part of the IoT realm or IoT field of research. So this is probably an example of that. Great. So the question is that this sort of applications, if we can use them for the communication between the cyclists, between the bicycles and the autonomous vehicles. I definitely can see potentials in that now that we are moving towards autonomous vehicles and connected vehicles. I think from the safety perspective, it's very probable that these sorts of, not specifically this application for activity recognition, but collecting data from sensors, including accelerometers and gyroscope, and then detecting activities that contribute to safety through machine learning, through prediction of any sort in artificial intelligence, could be useful in that area. I definitely think that the current algorithms that are used in autonomous vehicle and connected vehicles take advantage of similar algorithms, right? So in future, I mean, this I am not sure about how, again, because transportation is not my field and I'm here to learn from you in that aspect. I'm not sure how advanced are the new bicycles, or how embedded, how many embedded sensors do they have, or how that Internet of Thing concept works with the new types of new generations of bicycles and the connected vehicles. But I definitely see the potentials for that, for the safety of the cyclists. Yes. Again, I mean, I love these ideas. Jay, let's go and start working on it.
So I actually kind of, it's a sort of follow-up question to yours as well. When you were talking about the location dependence of your sensor data and your algorithm is trying to figure out what it's doing where, it seems like a lot of your data was dealing with a very closed off space. You were going to be dealing with data points in that space. How does this method extend if you are no longer sure that you are bound to a specific location? Does it work if you're on an open, like if some data points start leaving and some data points start entering? Does the method, do you have an idea how well the method still works in that situation?
Good question. So the question is that what we have done was in a controlled environment and in a lab setting. So how this can be extended into a real world situation where you may lose some data or you may not have the clean data that you want. That's the question that I usually get from the reviewers of my papers. This is a prototype. This is a lab scale experiment. When you enter the real world, you definitely have a lot of uncertainties that are not captured here. So I agree that you may lose some data in the environment that is not controlled. People may just take off that wearable sensor and don't use it for quite some time. But what I'm saying is that this is to show if that works. So
I think my question was more about the location dependence. If you have
the location. So you meant by entering into the zone and living, you meant the location aspect of it. Okay.
Lab environment, but maybe you have, instead of a closed system, you have more.
Okay. What I believe myself that this system shouldn't be dependent on location. The experiments that we did were not dependent on location. The only data that we used was accelerometer and gyroscope. So because of all these uncertainties that come with locations, these systems, again, are not location dependent, and I don't think a location dependent system, while it may add or contribute, add to the accuracy, but at the same time, because of all these things that you just mentioned, I don't think that's a good idea to at least exclusively use GPS data or location data for these kind of applications. Other questions, ideas?
observations of the actuals.
Great question. So the question is that in these experiments, we saw what's happening and we trained the data using this information. We saw that, okay, at this point in time, that specific worker is hammering, and we called it hammering, and we trained our algorithm. This makes it dependent on someone to label this algorithm, right? This is your question.
Yeah, it's what the labeling portion.
Exactly.
That one that comes around.
Yes.
But it's a necessary thing.
Yeah.
To use this sample.
So yeah, so first of all, I think I forgot to mention that yes, all these experiments were videotaped, and we annotated the data using those videos. So that is the non-automated part of this automated, or the framework that is claimed to be automated. The reason is that the algorithms that we use, machine learning algorithms that we use, are all supervised machine learning algorithms. If you want to have an algorithm that doesn't do this, I mean, you want to remove that manual part, you should be using an unsupervised machine learning algorithm, or a semi-supervised where you intervene just a little bit to give more prior knowledge, right? So the science of activity recognition or state recognition or state detection hasn't progressed that much yet, hasn't advanced that much yet, in order to be able to produce robust algorithms that can do these detections without labeling, without supervised algorithms. But this is definitely, it has been always on my wish list to try to come up with some sort of algorithm that does not depend on manual labeling or on manual input. In terms of the labeling. So if K-means is unsupervised, if you can come up with some sort of algorithm like K-means that can itself detect activities based on a high, in a high dimension space, in like 10 dimension space. This is what I'm thinking out loud right now. That could be the solution to the problem that you're raising here, right? So there might be solutions depending on the fact that you have a lot of data, and by a lot of data, I don't mean just the quantity of the data, the quantity of the types of the data that you have, different data modes. If you have that, and if you have the luxury of having different modes of data, and a lot of data now in terms of quantity, I don't think it's impossible. So again, that's something that can be explored in the lab setting where everything is controlled, and you can collect as much data as you want. But that's actually a very good point. So all these systems now at this point require someone to train them, require someone to label them. Now it happens so one of the machine learning algorithms that we deal with on a daily basis is in our email accounts, where spams are detected and are categorized as a spam in the email account, in the email inbox, or they're categorized or distinguished from the regular emails. These are also supervised algorithms that people who develop these algorithms train those algorithms that, okay, if you see this sentence, congratulations, you won $100,000 in our raffle. So this is a suspicious email, and based on the training, if you see these sort of words, these sort of patterns, then label those as a spam, right? So this is something that we are dealing with on a daily basis, and this is still supervised. Now, it doesn't have to be an unsupervised algorithm that is a robust algorithm. We can have something like this that we have in our Gmails that work if we can simulate all the activities that can happen in a transportation system or in a construction environment. But that's almost impossible. So that's the difference between a structured environment such as an email environment than construction. So while I think it is doable to make an unsupervised machine learning algorithm that works in such environments, it doesn't have to be. You can have a supervised machine learning algorithm that does a good job, but at the same time, if we can do that, that would be great. I don't know if I answered your question.
all the levels and all the experiments you talked about, the neural network architecture was the one that was most advanced. Do you know? I mean, I understand that part of the beauty of the neural networks is that you don't need to understand exactly how it works. But do you know why that architecture in particular was best suited for what you were trying to do with it versus all the other ones you were trying?
First of all, the question is that why neural network was the how why other machine learning algorithms were not as good as neural network? Because usually neural network is seen as a black box that you don't know what's going on inside. First of all, I knew what's going on inside because I wrote the code myself for the new. I mean, I used some of the existing codes, but I changed everything. So I knew what's going on inside, and that was actually the only algorithm or one of the ones that I actually knew exactly what's going on inside it. And probably that was the reason why it happened. For the SVM, I actually used an existing library. I didn't really care. When I saw that my neural network code works and works better than the SVM, I didn't dig into the SVM that why that system is not, that algorithm is not working as well. So no, I don't know why. Well, neural network is a higher level algorithm than a decision tree, which is very simple how it works, or a k-nearest neighbor, which is again a very simple algorithm. So I know why neural network is better than those two, but I don't know why neural network performed much better than SVM in this case, because I didn't actually I didn't go into the details of SVM, the support vector machine. Simpler algorithms, again, logistic regression is very simple. KNN is simple. Decision tree is simple. So I know that, okay, neural network is better than those. It's clear. But neural network and SVM, I really didn't know that. Sure. What do you mean by bad data?
For example, let's say in our transportation networks we have two data,
Mm-hmm.
and we use those data to, let's say, find the traffic flows and but we have to deal with these data. For example, we want a detector would show some volume but zero occupancy, so it's a bad data. So for example, I know about the route detectors, but I don't know about mobile data, accelerometers, and do they tend to get erroneous bit timing or degrade bit timing?
Okay.
If they do you actually have some system in place to actually figure it out?
Well, the question is that if we have bad data or bad data points in our data set that we collected, do we have any system in place, any strategy, any mechanism to rule them out or basically detect them at least? One of the steps of these algorithms was data preparation here, where we did to some extent, we did some data cleaning. So we removed outliers, for example. Those data points that we knew that this is junk, this is not part of what I need. So we did that. I remember that we have done some filtering as well for the data, low band and high band filtering. I don't know the technical details of this because again I used some existing libraries to do that. But that was the extent to which we did data cleaning. Now, what happens in terms of accelerometer? Yes, there is the problem of drift in accelerometer data that sometimes that happens. That was why I appended accelerometer data with the gyroscope data to some extent take care of that problem. But that was the extent to which we get in terms of cleaning the data or removing bad data, as you put. We cleaned the data to remove the outliers. We tried to do some filtering and as well as adding the gyroscope data to that. Thank you.